Hi students, this is Mrs. Gerstner doing a quick video review of coefficient of friction problems. So I'm going to go through an example of each type that you've been working so that you have an example. So we're going to start with a 500 kilogram car on a flat road at constant velocity. So the surface that the object is on is flat. I'm going to put my object on that surface. There are 4 forces acting on this car. There is 1,000 newtons of applied force. The car's weight aims perpendicular to the ground. Remember that weight is mass times gravity. So 500 kilograms times gravity gives us a weight of 4,900 newtons. Friction opposes the motion of the car, and normal force is the supporting force from the road. Constant velocity means the net force is 0. Therefore, the normal force equals the weight force and is 4,900 newtons. The applied force equals the friction force and is 1,000 newtons. The y's cancel out, the x's cancel out. Coefficient of friction is the force of friction over the normal force. So you've got 1,000 newtons divided by 4,900 newtons, and that gives you a coefficient of friction of 0.204. Similarly, in this one, we have a baseball player sliding into second base. He slows down because of the friction between him and the field. The field is flat. So here's my player. The only force acting on him along the ground is friction. He has weight, and the ground has to support him this way. We have an acceleration rate. That means he has not got a net force of 0. But his net force is his mass times acceleration, and it's caused by his friction. Weight and normal force will balance out and equal his mass times gravity. So the coefficient of friction in this case is the friction force over the normal force, and we can replace friction with mass times acceleration because the friction is his net force. Because normal force equals weight in this case, we can replace it with mass times gravity. The mass of the baseball player is irrelevant. It cancels out in our equation. So his acceleration rate is 3 meters per second squared. Gravity is 9.8 meters per second squared. And that gives us a coefficient of friction of 0.306. Now let's move on and add some angles in. When you have an object moving along a horizontal surface due to an applied force at an angle, the object itself is still on a flat surface. So in this example, we've got a stroller. It's 15 kilograms. We're pushing it forward by applying a force down the handle. That is 70 newtons. This handle makes a 30-degree angle. The mass of the stroller is 15 kilograms. Mass times gravity, 15 times 9.8, gives us a weight of 147 newtons. If we break this 70 Newton applied force into its x and y components, the x side is 70 times the cosine of 30 degrees, which is 60.6 newtons, and the y side is 70 times 30 degrees, which is 35 newtons. Now, speed is constant, so the net force is 0. That means the friction over here that is opposing the motion must equal the x component and is 60.6 newtons. The y component of our applied force is down. So as far as the ground is concerned, it must hold up more weight. The normal force is the actual weight of the stroller plus the y component of the applied force. So we take this 147 plus this 35 newtons, and we get 182 Newton normal force, or apparent weight. Coefficient of friction is the friction force over the normal force, so 60.6 divided by 182 gives us a final coefficient of friction of 0.333. Similarly, if we drag an object behind us like a wagon, here's my wagon, the only difference now is that the applied force is up and away, pulling the object along. We have an applied force along this handle. We've got a 30-degree angle. We are given that the mass of the wagon is 15 kilograms. We're dragging it behind us, and I'm giving you the apparent weight of 100 newtons. How much force is applied along the angle? Based on 15 kilograms times gravity, we have an actual weight of 147 newtons. I'm telling you that the normal force is only 100 this time. Normal force is apparent weight. When you apply a force up at an angle, as far as the ground is concerned, the object seemingly got lighter. So it's the actual weight minus the y component of the applied force. So if we know normal force is 100 newtons, and we know weight is actually 147 newtons, we can figure out that the y component is 47 newtons. So if this side of our triangle is 47, the sine of 30 degrees is 47 over the applied force, and our applied force is 94 newtons. So that's the basics of objects moving along a flat surface, and then we have inclined planes. So I've got a couple quick examples of inclined planes. Here we have a sled that is 20 kilograms accelerating down a ski slope, incline of 40 degrees. So my surface is now an incline with a 40-degree angle. I'm going to put my sled on that incline. Always a component of the object's weight is trying to pull it naturally down the incline. So, given the mass of 20 kilograms, multiply 20 kilograms times gravity, and we know that we have a weight of 196 newtons. That natural pulling force down is weight times the sine of the angle. So 196 times the sine of 40 degrees is 126 newtons. And the normal force is the force pressing the sled to the incline. That is weight times the cosine of the angle. So 196 times cosine of 40 degrees is 150 newtons. Now, you are accelerating. So there is some friction, but you're still speeding up. So you have a net force that equals the mass times acceleration, and it's the difference in the forces acting along the incline, the one down the hill minus the one up the hill. So we've got a mass of 20 kilograms times an acceleration rate of 3. We know the FP is 126, and we can use that to determine how much friction there is. In this case, 66 newtons. Now we can figure out the coefficient of friction, which is the friction force divided by the normal force. So 66 newtons divided by 150. That gives us a coefficient of friction of 0.44. One more example. You have a bike. You're riding it. You and your bike have a combined mass of 75 kilograms. I'm giving you the coefficient of friction is 0.35. You are riding up the hill, which has a 15-degree slope. So again, there is my slope. Here's you and your bicycle. You must apply a force up the hill. Working against you is the part of your weight, the FP, that naturally goes down the hill. And since you are moving uphill, this time friction opposes your motion and is downhill. We're dealing with constant speed, which means our net force must end up being 0. So let's start with what we know. Given a 75 kilogram mass, 75 times 9.8 is 735 newtons. FP is weight times the sine of the angle. So 735 times the sine of 15 degrees gives us an FP down the hill of 190 newtons. Normal force is weight times the cosine of the angle. So 735 times cosine of 15 degrees is 710 newtons. Now, because the net force is 0, the forces up the hill, which is applied force, equal the forces combined down the hill, which is friction plus the pulling force. So the amount of applied force is 200. Oh, I forgot to solve for friction. Sorry about that. Coefficient of friction is friction force over normal force. I gave you the coefficient being 0.350, and we know normal force is 710. This is how we find the friction force. 710 times 0.35 is 249 newtons. We're going to use that up here when we solve for our applied force. The applied force up equals the sum of the two forces down. So our friction is 249 newtons plus our pulling force is 190 newtons, and that gives us a total applied force of 439 newtons.